Okay, maybe we're gonna start now. So good afternoon, everyone. So welcome to the very last talk of this very nice workshop. So we'll have Gabriel Menezes from the Universidad Federal de Rio de Janeiro and the Institute de Física Teórica, who's going to tell us about the Compton Scattering Amplitude in field theory and string theory. So please.
Well, thanks, Fabian, for the nice introduction. Thanks, Ricardo, as well, for the opportunity. And it's been really great to be here for these 3 weeks.
Oh, it's me.
Oh, it's you.
I'm just checking with some people are asking.
So continuing, it's been great to attend to all those interesting talks and interesting conversations that I've been doing to hear, but I understand that I started up. So I'm not going to bother you guys for a long time, so let's get going. So this is the outline of this talk. Great. So I'm going to talk about a little bit of generalities before we get to the point, and maybe we get to see some interesting stuff. Okay, so let me give you just a historical background. Compton is this guy here that we've been discussing about. That's the guy. And traditionally, we talk about the Compton scattering as the scattering of a high frequency photon with interaction with a charged particle. That's the traditional sense of a Compton scattering. And historically speaking, it demonstrated the particle nature of electromagnetic radiation at that time. And the low energy limit, it's famous known as a Thomson scattering. So in our Feynman terminology, we would say that at tree level, the Compton scattering goes by those 4 diagrams. Of course, this diagram is only present when we are considering gauge bosons that self-interacts, which is not the case, of course, in electromagnetism. So, what do we really care about Compton? I mean, why is that so important for us? Well, we can list a lot of examples. I just list some of them here. But the key message here is that Comptons are really important to understand Kerr amplitudes, right? And for instance, if you go to a one-loop calculation, you see that if you're calculating the amplitude using, for instance, generalized unitarity, you need to calculate a Compton amplitude, a true-level Compton amplitude. So you have to worry about that. Also, if you are interested in studying the K-Mach formulas, maybe you want to study the scattering of waves of curved black holes, for instance, or any black holes, or any astrophysical massive objects, you find that at leading order, you also have to calculate a Compton amplitude. Even if you want to calculate the leading quantum correction, say for the bending of light, you also be in front of a Compton amplitude that you have to calculate. So it seems like a great idea to understand it and what challenges can be made in the calculation. So, of course, what we are using here, we are using here the so-called effective field theory of gravity, because what we want to do here is try to extract the classical part from a quantum amplitude calculation. So we know now quite a long time that general relativity could be envisaged as a fundamental quantum theory. Actually, an effective field theory, but the main message here is that it doesn't make real sense to quantize everything but leave gravity as a classical field. It doesn't make any sense. So the modern view, if you can put it this way, the modern view is try to start up from quantum field theory and try to understand how we can extract the classical part, how we can extract the classical physics from quantum physics. Actually, the idea is try to probe the correct kinematic region. In this correct kinematic region, you will find the classical physics as well. And so, how do you do that? We know that at tree level, we expect to find classical physics. What is a very quite interesting thing is that you can also extract classical physics from loop diagrams, right? And in a quantum field theory description, this has to do with the infrared behavior of Feynman diagrams involved. Actually, you can do just the following. You just take, for instance, a dispersion integration, using the name as you want, like a Cayley-Lehmann representation for a two-point function. And then you see that when you're working with massless particles, you're considering interaction and exchange massless particles, the threshold of the dispersion integral is allowed to vanish. And that is the key point, so you can see that there are classical contributions coming from that. So that's the infrared behavior that's behind this. But the general recipe is, of course, search for non-analytic contributions. So that's the main idea, right? So these are, I mean, there are a bunch of papers that I can quote. I just quote these two. But this probably is the first paper to call attention to the community that we can really extract classical physics from a quantum calculation. But there is also these two interesting papers here. This paper by Sphere, Radu, and everybody else was meant to calculate the classical potential at 3 p.m. So it's a loop calculation, right? And if you want to calculate directly observables, you can use also the so-called K-Mach formulas, which is a very interesting formula, which allows you to do things from directly the amplitude. So you also have a recipe to extract the classical part from this. But okay, but let's get more specific. Let's talk about black holes, right? So there is no hair theory, and because of this no hair theory, we can think of black holes as elementary particles. Of course, we can be more technical at that stuff. So the idea here is to try to construct a three-point amplitude, which in the classical limit reproduces what you expect from curved black holes as well. But what about if we go to higher orders or higher point amplitudes? When you do that, you immediately find that you need the Comptons in your calculation. Okay, so these are the building blocks for electromagnetism. This is the three-point amplitude of mentioning you guys in a massive spin analyticity formula representation, and I already gave you the Compton amplitude that you calculate from this guy here. And I'm putting here this expression, which is valid only for spins less or equal to 1 in case of electromagnetism. You can do a similar calculation for gravity as well. Just for instance, you can use a double copy, right? And the idea is that the Compton amplitude calculated from three-point amplitude also has a maximum spin, which the representation is valid. And here I call the generic three-point amplitude, so we can see that the so-called minimally coupled amplitude concerns only this guy here, not all of these guys here. So in a sense, when we talk about the minimally coupled three-point amplitude, we are talking about the simplest possible amplitude coming from this three-point generic amplitude, right? Okay, but there are constraints that tell us that this is the right choice. one constraint comes from UV. That amplitude has good high energy behavior. You can prove that. But also you have a constraint from IR. That amplitude in the classical limit will also reproduce the Wilson coefficients associated with the curve of force. So we're good here, right? But the point is the Compton amplitude. That's the point here. We want to understand why this amplitude is only valid to spins up to s equals 2. Right? So what's going on? What you can do is, try to expand one of those expressions and see what happens. When you expand, you will find that this guy here will generate a spurious pole. And why we call that a spurious pole? Because it's not associated with any exchange of particles. And last time I checked, at tree level, the only singularities that we have are poles associated with cut propagators. And this has to do with the exchange of particles in your spectrum. Of course, the problem that the thing that you have a spurious pole is not exactly the problem, because it might have a zero residue. I mean, if you calculate amplitudes from BCFW recursion relation, you'll find also that you have spurious poles. But all those spurious poles have zero residue, so you're fine with that. But it's not the case here. It clearly has a non-zero residue. Okay, so that is definitely a problem for quantum physics, but if you are a classical guy, you might argue that, okay, I don't care about classical physics, quantum physics. I want to know about classical physics. Okay, so if you use
you start having negative energies, that would be a problem with classical.
yes, also, yes. So, in summary, we have a problem. And you want to solve all, or we want to understand what's happening, at least. Okay, so let me give you a key observation. It's one of the ways that you can think of where did it come from. Right, so consider this Lagrangian. It's a SUN version of the Lagrangian given by those gentlemen here. And in this Lagrangian, they didn't consider transverse field, so this is an unconstrained field. Okay, but in any case, you can fix these coefficients, these Wilson coefficients, by imposing the root curve solution. They are just one, as in the curve solution. So, if you calculate the 3-point amplitude in a standard fashion, Feynman rules, just do the usual recipe, you will find after using on-shell conditions and 3-point special kinematics, the same 3-point amplitude that I put before. So it seems that when you try to construct Compton amplitudes, say, by consistent factorization, starting from this representation, you will find this result. So in this sense, you will have to take a step back and not use a 3-point special kinematics representation to get, I don't know, a healthy Compton amplitude. And the same argument you can apply to gravity as well. This is just electromagnetism, but you can apply it to gravity as well. Okay, so I'll give you two possible solutions. Okay, so we know that consistent factorization doesn't give you all information or all gauge information that you can get from the BCFW as well. BCFW to work relies on the fact that 3-point amplitude should furnish you all gauge information that you need. If you have a theory that has extra gauge information that cannot be captured by cuts of the propagator, then you don't expect for them to work. So it might be the case here. So it seems that we might have a bunch of contact terms available to consider, and then why not using them to try to cancel the screws? Well, this is a possibility, but the problem is these contact terms come with arbitrary coefficients in the Lagrangian. So you have to fix these coefficients. So how do you fix these coefficients? Well, one way is to use physics, right? And one way that you can use that is this cute observation. This is also a cute observation. If you go to up to 2 p.m. order in the calculation, you will find that the structure holds just like that. You have an amplitude structure. Q is a momentum transfer, A is a rescale spin vector. And this guy, this structure is associated with this shift symmetry. So we know this is valid up to 2 p.m. order. So why don't we assume that is valid to all PM orders? So when you do that, you have a guy that can help you to fix the arbitrary coefficients. Of course, that's not only ingredient that you need, but that's an important ingredient. And then you can do that. And then you find Compton amplitude that looks like this.
Sorry, so the cubic action will fix part of the quartic action? Is that what you said?
The cubic action? No, contact terms.
So it's at every order in perturbation. So it doesn't relate to different orders in the expansion.
No, you just add the contact terms here. These are the contact terms. These guys here. And these guys do not, they are not captured by the cuts in the physical channels. So when you cut, you get the 3-point amplitudes that you expect to get in the factorization. So you're good. But they cancel the residues associated with the unphysical poles. So if you, let's say, we want to calculate the unphysical pole, so you cut the unphysical pole. So you have the residue. This residue is exactly canceled by these contact terms. Of course, this is an intricate attempt to cancel. And then you also have this arbitrary coefficients here. And then how you can fix it? Oops. You can fix it using this guy here. You assume that the structure in the end, in the classical part, has to have something like this. And it's important. This is the classical amplitude that has a structure, not the quantum. Okay, so this is one way to solve the problem. Impose spin shift symmetry. there is also one other way, very interesting way to try to solve the problem, which Fabian, especially Fabian and Justin just told us a few days back. And the idea is, okay, we're not going to use spin shift symmetry. We can use spin shift symmetry, but we're not interested exactly in it. We are interested in trying to understand solutions to two costs. And then we're going to see if those solutions can help us fix the coefficients given in the contact terms. So this is the main idea. Actually, they are part of solutions that do not preserve the spin shift symmetry. In a quantum field theory language, what is happening here? What's happening here is that the factorization, the S and U channel is not the same as before. So it seems that you have additional states propagating here besides curve, when you are considering the first zone solution. So this is a very interesting part. So this is the guys that are generating the contact terms with all these arbitrary coefficients. And these coefficients are fixed here by looking at the solutions to Tolkowski equation. For instance, you have a very interesting table which relates everything that I've just said. How you fix those guys here. Those guys here comes from the Tolkowski solutions, and the C's are just the C's in these in here. There is another way to fix the problematic Compton amplitude.
So, the factorization and the S and U channels
Are different.
different from what?
Different from the 3-point curve. Yes,
Yeah,
the T channel is okay, but the S and U channel.
maybe it's, yeah, we clarify, like, that happen only in the two parts.
Yes.
The throwaway part is the Tchaikovsky solution. Of course, if you consider the full solution, then
It's okay.
it's just some people near some.
Red, blue,
side.
Yes.
Yes.
Yeah, then we can interpret as additional states besides her.
Yeah, but we don't have to-
interesting.
You don't have to do that.
We did not do that. I mean,
We did.
Oh, no, you get, yes, you fix it now.
okay.
Okay, so we have two interesting formulas that fix the Compton amplitude in different ways, but they don't seem to match, generically speaking. You might make them match, but in a generic basis, generically speaking, they don't seem to match. So can we try anything else? Can we try another type of calculation and see if we can decide if which one is correct, or if they are both wrong, or if they are both correct? So one thing that we can do is go to string theory. Why would we go to string theory? Because, well, it's a theory that has the generate amplitudes with good UV behavior. It has a massive tower of higher massive spins, higher spins, massive higher spins, massive higher spins. So it could be a good candidate to try to tell us what is going on with this amplitude. But hold your horses, because things are not simple. We have some subtleties here. So for instance, if you go to the 3-point amplitude, if you calculate the 3-point amplitude from string theory, you will see that it is, as we can call, maximally complex. So it generates all those terms in the 3-point amplitude that I
So which computation are you talking about in string theory?
two massive guys with generic spins and one massless boson, a 3-point amplitude from that.
At generic level,
A generic mass level.
is this
Yes.
bone?
Yes.
Never seen this before.
Yes. Yes. In the Nouveau-Schwarz formalism, in the Nouveau-Schwarz sector. Yes, you can do it. So, of course, string theory do not generate arbitrary coefficients. So it generates, apart from some combinations of S and alpha primes in here for G0, G1, and it generates everything here. So it's not just this guy. So this is what I mean.
Yes, so is this for DDF states or for single particle states?
Single particle states. You just take the correct vertex operators, calculate the correlators, and shoot. That's what you got.
I want to show this one.
Yes, I can show you after that. Okay. So other thing about the 3-point amplitude is that if you take the classical limit, 3-point amplitude from string theory, if you take the classical limit, it doesn't seem to describe current amplitude. It describes something else, right? So it doesn't seem that things are good if you start from string theory, but let me show you now that.
I'm
Yeah.
very interested in this process.
Okay.
So, are you talking about the leading edge trajectory?
Yes, leading edge trajectory.
But the leading edge trajectory, I thought that it violates the curve bound, so you can never describe a curve black hole.
For the age, yes,
Some
the
speed
age,
draw,
yes, yes,
There's a work
yes,
of like Empara,
yes,
Empara,
yes,
Empara,
yes,
Empara.
yes, yes. At 3 points, but at 4 points in Compton amplitude, you got a surprise.
Okay, because I thought there has to be someone in the middle, so you go to high level, but it has to be in the middle of the spectrum, some crazy tableau.
It could be, but it could be, it could be, it could be, it could be. But there is a surprise here. An unexpected surprise, but anyway, but you're right, there is also those things. I put here the gravitational quadrupole is different as well from the one calculated from field theory. Okay, so this is just a little bit of string theory. I'm not going to bother you guys with all technical details, but the important part here is the vertex operators that we use to calculate the amplitude. So these are the vertex operators that we use. This guy here is going to be associated with the higher spin massive states. And this guy here will be associated with the massless boson, the photon, or the gluon, if you're talking about a non-binary gauge theory. Okay, so what's the amplitude that we want to calculate? That is the guy. So we'll just plug in the vertex operators, do the calculation. It's a huge calculation. Separate the physical channels that you are interested in, and you find this cute amplitude here. This is for the S channel, this is for U channel. I didn't call those 4 guys here because these expressions are huge for this generic mass level, right? But here's to mention just that we put just in 4 contributions because we have different number of fermions associated with the correlators in here. So this guy here is associated with 6 fermions in the correlator. These 2 guys are associated with 4 fermions in the correlator, and this guy here is associated with 2 fermions in the correlator. This representation, it's easier to prove the water identity. So it's just a convenient way to express it. Okay, so let's try to understand what's happening. So say you want to calculate the massive spin-1 amplitude from that guy here. So we have to take an adequate soft expansion, and then the final result is this guy here. You can write this guy in terms of Lorentz generators, and then you find the same expression that literature has quoted before. So yes, as Guilherme was telling us, you don't expect that these amplitudes would reproduce in any sort of way current amplitudes, but nevertheless, if you go to the, let's say, probably the simplest non-trivial case, which we know that they are not spurious poles. This is an amplitude coming from the open string theory, so electromagnetism. But it's a sense check, right? Just to see what's going on. And then we obtain what we were expecting. I mean, not what we were really expecting, but if we want to say that, okay, these amplitudes should, if we, with magic, I don't know, but if you wanted to use this amplitude to study current amplitudes, you would expect to find this term, and we did find this term. Okay, so what would be the next steps in here?
One question, like, you can show the contact term in the previous slide. I guess it derives somewhere from those terms that you did in the previous slide, the one from the, yeah, STU, the contact.
The contact terms are within one of those guys. They're just mixed it up.
Ah, you didn't write it.
Yes.
Okay.
Okay. But you can extract the contact term and then it's just one of those guys here. Let me see. Here.
Okay.
This is the contact.
Yeah, that's right. Okay, perfect. Yes.
What about the 3-point?
The 3-point amplitude doesn't seem to describe
From the leading edge trajectory.
yes.
It definitely is not that you mentioned in the paper.
Not for generic space. Not for generic space. You can do a specific choice to make for a determinate spin to match the curve solution, but generically speaking, it doesn't.
I've never seen a sharp claim in the literature, but what I heard from around the orbit of Vecchia, also Massimo Bianchi is telling me, probably if you take the middle of the spectrum and take a specific admixture, then you can make it work. But pure single particle states, nobody knows.
But that's a surprise. You don't expect that. I mean, you expect that any amplitude at any mass level to reproduce an amplitude that you will obtain from field theory trying to describe curve amplitudes. I mean, this is root curve, so this is unexpected. So the next step here is to go to the next mass level and see what's going on. And the next mass level is interesting as well because you can use this guy and the n=2 mass level to double copy into gravity and explain in gravity the spin-3 case. And the spin-3 case, when you extract the classical counterpart, is going to describe you the classical spin vector up to the 6th order. And then you can compare with those guys in here.
Sorry, let me just try to understand. So at 3 points, you cannot get something. So the external states don't look like a black hole.
Yeah, classically speaking, it's a classical.
But now you compute the scattering, and then there's all sorts of strange junk that goes to the middle, and it reproduces all black hole.
At massive spin 1, it's not the generic part.
So somehow the magic of all the string states is reproducing something.
Yes, and why is that? We don't know yet.
Is this leading edge?
The leading edge trajectory. Just the leading edge trajectory.
Outside, right? Outside, but you still exchange.
Still exchange, exactly. And of course, this is the quantum pass. We also have to take the classical limit to compare it. Yes. Yeah.
How is it consistent when Compton Amplitude to be like this? But then
The 3-point amplitude.
Yeah,
That's a great question.
Factorization.
Yeah, but in string theory, factorization is different from quantum theory because you also have this tower of massive state. So it's not that simple.
Or you just flew a bunch of 3-point
Yes.
amplitudes, right? Infinitely many.
Exactly, exactly.
In fact, nobody remembers.
Exactly, exactly.
Because
Yes. Yeah, that, if you do that, man, get 100 citations in the next day. That is a very interesting thing to understand. That's the point. Maybe you have a bunch of 3-point amplitudes that we are not considering when you're just considering one particular 3-point amplitude that are giving this additional information. So in a way, the massive spin 1 amplitude works. Of course, I'm not saying that if you go to the next level, everything is going to work as well. I don't know. We have to extract this part from the generic amplitude and see what's going on. But
what do you get then if you take just 3 vertex equations? What do you get if you only consider 3 vertex equations?
the 3-point amplitude.
Yes. What happens?
In the classical limit, you mean?
Yeah.
You retain a classical string.
So there's some
3-point amplitude in classical limit. A classical string with an end that is charged. That's it. It's not. It's not.
This 3-point in the results.
Curve.
Yeah.
Yeah,
That's not bad.
It doesn't match any of
It doesn't.
I don't know much where the one
It's
is
spin 2.
But spin two.
It's not 2.
Even the linear and spin term, right? So the linear is it G2 or does it already disappear there? You know, like the.
The 3-point amplitude mean.
Yeah, so this
For spin 1.
for spin 1, classical limit,
Yes.
linear and spin term.
Here are the 3 points from string theory.
3-point from leading branch string theory. In like
Spin 1, spin 2, I know that he agrees, but spin 1, I don't remember. I'm not sure. If it is. Probably.
That is very universal, so.
No, yes.
I was
The
wondering-
coefficients are not universal, actually. You have to take large spin limits.
No, yeah, yes.
Oh, that's right.
You have to take large.
That's my power.
Yes. You have coefficients depending on the spin, right? So we have to take one very specific spin to have the coefficients not depending on the spin. It's a very specific choice.
The other thing that's a little bit confusing here is that, before you take the classical limit, then there's different operators you have in effect. So in fact, even consistent Compton amplitudes it's not unique.
Yes.
And I'm not saying that, but yes, here, that's not how the.
That's
the big model.
yeah. Probably changed. It could be, but that's a very good thing to imagine. That would be very interesting to see how that communicates
I don't
with
see
these.
those degrees of freedom, they're
Yes.
the degrees of freedom corresponding essentially different, having different operators. Effective operators.
In the effective theory.
Not in the effective
Oh.
theory, because out of the string theory. Because the Compton amplitude is a higher spin, in some sense, it's below the mass of this, of the particle. There are many possible operators.
Yes, of course. Yes.
But there's only one.
No, there's a possible limit, there's only one interesting match curve. But, okay, you haven't taken the classical limit. Yes. And so, why did you take the classical limit in this one? What is so special about?
Yes. But yeah. I'm not saying that I have a word.
Sorry, I don't understand. Can you say again what you completed?
Well, I mean, for higher spin, part actually means spin 1 and spin 2 rather than there's not a unique Compton amplitude. It's higher, it's sort of operating. So the main thing, the most naive thing about that is just to make it consistent. But then there's more than one coupling. So therefore there's more than one amplitude. Here I've seen just some particular amplitude. Yes. So I'm not understanding.
What is the
The claim is that you're able to produce a quantum consistent.
Yes.
Why this particular one?
There's one string theory. And
Well, they're actually.
I think they're different. Yes, yeah, I think I would compare with an FT. Yes.
Portfolio.
Yes, yeah, sure. I think I would compare with an FT. Because you have so many, as you said, you have so many possible quantum amplitudes. And then I would compare with an FT.
You're taking a specific string, right?
It's an option.
so, yeah, I mean, I
Yes.
guess good point there. There are different string theories, I guess, with
But, I'm not seeing that those degrees of freedom match the.
Yes. It's not straightforward. It's not straightforward.
Oh, but the way to go would be to compute this in other string theory.
Yeah, now the string theory, you can do that, or you can compare with an effective theory calculation. To see, okay, this is the guy that talks to this calculation.
The guy who's treating this theory?
No, effective theory, not effective theory of Austrian. Effective theory.
Well, that's what we.
Like the paper that you just submitted on. Like that one. That would be a great idea.
I mean,
Well, they are. This
In a sense. Yes. Okay, guys, so I promised you that I wouldn't hold you so long since we are very tired. So let me give you just the outlook of this here. So what are the questions? Is spin shift symmetry really valid to all orders? The spin order is just a acute observation valid up to 2 p.m. The approach coming from the solutions of Minkowski equations seems to be very promising. But we have to understand a little bit some other things concerning the analytic continuation that those guys have to do to compare with the quantum field theory computation. And string theory is certainly teaching us something, but we don't quite know what it is that it is teaching us. So perhaps considering sub-leading Regge trajectories is a good idea, of course, but you can also go to a pure spinor computation, which is a lot more difficult, but in principle, you will furnish a lot more information for us. Nevertheless, these are wonderful times to discuss all those things. So I'm ready to take questions. Thank you, guys.
Thank you, so do we have any further questions?
Yes.
Already started about this but I missed the point. This spin shift symmetry, yes, this when you get this result, I mean, you should have this.
Well, the idea is that when you do the calculation, you're studying scattering of massive states that classical amplitudes private curve black holes. So when you go to 2 p.m., you see that the classical amplitude has this structure.
comment.
You can do it, of course.
So yeah, up to 2 p.m. Yes, but I mean, more point is if. Okay, so we used to have this conjecture in numbers up to spin to the fourth, but now I think we can consider it converged by our.
Yes.
And up to spin to the fourth, the Compton amplitude, so it can also be expressed in terms of like the two-body amplitude. It's really like a property of the Compton, which enters the 2 p.m. calculation.
So this amplitude,
Anyway,
this amplitude
it's
is
just observed to hold up to spin.
and this amplitude has that symmetry.
They say that beyond significant, it's not there.
According to what we did.
Yes, yes, again, according to them,
So it should be an accident here too, if you're going to match the, but that's a statement of curve.
yes,
If you're going to quantum theory, you could impose that. It's interesting, and this speed off in some other directions and try to.
yeah.
Also, just, by the way, like, doesn't, like, in the work by now, and I'm really, I don't know, at 3 p.m. spin squared, it does not go.
It wasn't, it's.
Well, it's just something that it's good up to 2 p.m. on, or good up to the fourth order. Up to.
As more seems to be a property in this opposite ellipsis.
Yes, yes.
It will be a competition between the three edges from contribution from those. So once we have the things now.
Yes.
It will be a property specifically of the opposite ellipsis.
Yes, you're right, and that's it. Yes.
I have a question. So you mentioned the pure spin-ons. Elaborate on what is the
That's a very difficult calculation because you know,
first of all,
so that's the main component.
I don't understand why, I mean, the amplitude is what it is, but some words in there.
Yes, yes, yes,
What do you do in the worldsheet? Okay, maybe make some life simpler, more complicated.
yes, yes.
Why do you think that pure spin is all about?
Well,
Pure spin is just making more symmetries manifest.
yeah, so
And we're seeing that in the worldsheet to be targets.
so I would say the following. At lower mass levels, you can construct vertex operators that in principle would contain all the trajectories. Of course, you don't know how to do that for generic mass. I mean, it could be anything.
What about the DF states?
That's a good question.
DDF states,
Yes.
it's just a coherent state.
Yeah.
Yes.
All sorts of strings.
Yes.
You could be aware this one.
I mean, the 3-point amplitude is known. I didn't know, or you can have to show me. The DDF states there is a form.
Yes. 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 No.
But it didn't use this. No, because the 3 point massive promotion. Okay, one by the first one. So it's 8 9.
8 9.
Yeah. So it's like a 2 random shorts, massive states, and then one. General structure.
But if, let's say, we do all those things with all other states in string theory, what we are losing, what is it that we are losing? What is it that string theory is telling us?
Well, first of all, it would be nice to have them just because.
Yes, yes.
If you want to talk about string amplitudes, you might as well start from 3-point amplitude.
Yes.
Well, second, because it may teach you something about this universal feature. This third, this question about is the generic. So we think that strings that strong coupling become black holes, right? But then weak coupling, do they have any resemblance to a black hole? It seems that the leading edge trajectory doesn't. So we don't want to get on this actually what's
What's the by the expression?
Other range trajectories, not just.
Yeah, not the leading edge trajectory. There are other things like different young couples.
Yes. Yes. Other trajectories in generic mass.
At a given mass, you can have many spins with many directions. That's a generic stuff. Could be that it couples to the graviton or even similar to or lasers, gravitational waves. I'm trying to do it, so that's why I was shocked that it didn't exist, because I'm trying to do it. But anyway,
But
light
at leading trajectories.
for any, no, for I'm trying to do for generic level.
Okay.
But then I go to light cone gauge because at 3 points, everything is fixed by symmetries. It's a theory of numbers in the end.
Yeah. Light is like engaged. It's
Well, that's too difficult, but I think it's doable.
It's doable. Light engaged.
But I don't understand. Well, maybe the question is too is why do you think what do you think your spinners will buy?
Well, just a way to try to encapsulate all those other leading trajectories, but you're right, you can consider those.
Also, another thing, you're leading just with the free level.
Yes, true level.
Seems to me that working with bosons would be easier. I mean,
I don't know, because you have the touching.
okay.
I don't know how we would interpret the touch.
I mean, he might have a interpretation, but
I don't know. I don't know. No, it's just, remember, there is a frequent competition, it's one massive and massive state, so it's two massive reactions.
Okay, no, that's fine. Calculation.
Actually, I guess the last question we talked. Maybe there are opportunities.
I'm curious how.
But tomorrow we meet.
Go for it.
Did you read the email?
Yes, about